So the data set that we're going to play with to start with in this lesson is a simple 2D data set, right? So what it means is your images are huge, right? Even for, let's say, 100 cross 100 image, you have 10,000 values in your vector, right? Because you flatten all of them out. But in our case, we simply have two numbers, x and y. And this is why we can plot it here. So our data may look like, so at 0, we have y equal to maybe, I don't know, 0.4, 0.3. So we have 0, 0.4. So this is one data point. Then we might have something like, 0.5, 0.5. So we have 0.5, 0.5. And then we might have 1, I don't know, like minus 1.3, minus 1.5. So it's 1, minus 1.5. But then at the same time, we again have this one as well, which is 1, 1.5, and so on. So these are our data points, right? So this is data point 1, data point 2, data point 3, and so on. And this is the data set that we are going to generate, right? So we will start with this, we will noise it, and then from pure noise we will try to generate samples from this data set. But our data set dimension is simply x₁₀₀, right? So our x belongs to this two-dimensional data set. So our x belongs to real numbers of dimension 2, right? So our x is a 2-long vector. And here in code, when you look at it, you'll see that we are creating data set with a very simple way. We kind of say, okay, we want a Swiss roll. We want about 10,000 samples. These are the standard default values. And then we say, if the data set is f-curve, then you do this. If the data set is Swiss roll, you kind of then call this function make Swiss roll. And these are ready-made functions. And then we simply use it, and this is all that there is in our data. So the data will have 10,000 of these two, these x, y pairs. And x, y is our data. That is our x. And now we talk about the reverse process. Okay. So what I want us to understand is we started with the forward process, right? So we started with an image x0 and we made it noisy. We made it, let's say, x₁₀₀, right? x₁₀₀ is really noisy and x₁₀₀ looks just like noise, right? It's almost like static noise. The good news is that we have maintained the variance. We have maintained the variance of x0 equal to 1, which is also equal to the variance of this above, right? So, and we also know a way to get from x0 to x₁₀ directly by putting in that recursive equation and then kind of doing some algebra and removing all things out, right? So we can then directly get to this x₁₀₀ or x any number, x500, x10,000 from x0 directly. So we know exactly how much to put because it's Gaussian noise, it's linear, and we could do that algebra. So this is all that we know till now. Now, what is this reversal process? Well, the reversal process is simple, but we'll go into some nuances, but I'm going to do a lot of hand waving and we're not going to go into too much detail, but I'll point you to all the right resources that you want to look into if you want to dive in deeper. So in the reverse process, what we're doing is we're saying, okay, we will have a neural network, right? And our neural network will basically take some x and some t, right? So let's say we give it x 100. We will also give it t 100 because and then it will essentially produce noise. It will basically tell me how much noise is in x100 for it to lead to x0, meaning whatever is the output, right? So let's say the output is E100, then my x100 minus this epsilon 100 should give me my x0. And this is the mapping that my neural network is learning. Okay, the neural network takes two things. It takes your noisy input and it takes your time step and it gives out the final noise in the final step. That is how you train it. Okay. So you train it like this, but this is not how you do inference. At inference, we don't want to go directly from your static noise to your final. We want to do it in 1,000 steps, right? So we want to go from your x₁₀₀ to x₁₀₀, then from your x₁₀₀ to x₁₀₀, all the way to, you know, x900, 800, 100, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So we want to do those 1,000 steps, because otherwise it's not stable, right? And you get, I think, intuitively why. So this is why we are looking at the reverse process. But the formula that makes this do is this, and I'm showing you this formula because we have this in code and we have to use this formula. But I'll not go into details of how we derive it. I'll point you to the right resource. And this is the right resource. If you want to really look into how this formula is derived, you look into this. Essentially, what we are doing is, we are saying that if you add Gaussian noise in infinitely tiny steps going forward, the laws of physics and statistics dictate that the reverse steps must also be Gaussian. And this is a very cool property. And through some Bayesian algebra, it's actually not difficult. You can prove that if your neural network predicts the noise epsilon theta, we can calculate the exact mean of the previous time step, mu theta equals 1 upon alpha t xt minus 1 upon alpha 1 minus alpha t upon under root of 1 minus alpha bar t epsilon naught. And what we are saying here is, okay, we want to go from xt to xt minus 1. Remember, this is the reverse process. So we want to subtract some noise. And then this is the variance business, right? There we were adding, so we were, you know, multiplying. Here we are subtracting, so we are dividing. And this essentially is what comes from that derivation, right? This is basically saying how much of noise should I reduce, because I know how to get to the final step. But then if you want to kind of, you know, just take one time step, this is how much it should be. And this comes out from derivation, and look at that video. And this Langevin dynamics is another non-intuitive thing that we do, where this helps with diversity. And what we are doing is, we got our xt minus 1 with your mu naught, right? But we are saying that to this mu naught, we will also add a tiny bit of noise again. And I know this bums you up because you just took noise out and then you're adding noise back. I know what's going on, right? But this is like lower noise, and this is for variety, so that it doesn't exactly go in that flow all the time. And in code, this is how we do the sampling, the reverse process. So you start with, let's say, you know, xt, and this is, you know, pure Gaussian noise. So it's essentially just sampling from your normal distribution with zero mean and identity variance. And then from t minus 1 to 0, what we do is we predict our epsilon naught, right? So our neural network, as you know, takes the current time step. So it takes your noisy image at xt and t, right? And what it gives, it predicts your you know, your noise at the current time step. And then what you want to do is, you want to remove the predicted noise, but not this fully, but from that formula, right? So not from just what the neural network gives, but then we put that thing, that epsilon naught, epsilon theta here, and then we do it iteratively. So let's look at, you know, so the code, and then finally, obviously, you return the x naught. So we set the model in eval because we are not doing any training. What we are doing is, we say that for our time steps, you know, for the number of time steps, what you do is you give me the predicted noise. So your model takes in your noisy image and the time, and it gives us the predicted noise. And now what we are doing is, we are setting these things up, right? And then what we are doing is, we are essentially doing this coefficient business, the mean business, right? So the mean is 1 upon square root into this, and this is exactly this. And then we are saying that we want to the noise and your mean into this, right? So into the noise, and this is what your xt is, or if it's the first step, it's the final step, then your xt is the mean itself. And then you again go to the top of the loop, right? So then you do this again. You again put, so now you're in the previous time step, and now you're putting the previous time step here, and your xt is essentially your new thing here, right? Your new thing here. So your xt is essentially your new thing from here. So though you get your final noise as output, you don't want to use it because you cannot use it. You want to use only a part of it, and you want to take one time step forward and keep doing that in this loop. And what does the training loop look like? Well, the training loop is quite simple. We already spoke about it. You sample a real data x0. So you have some input image, let's say, or input audio, or input 3D shape, or so many different things, input speech, etc. And then what you want to do is, so the goal is obviously to predict noise. So for the given noisy image, you want to predict how much noise it contains. So for that, you sample your data point and you pick a random time step, let's say 300. Then you jump directly to 300 using the reparameterization trick that we learned. You feed your xt into and t into the neural network, our simple MLP. I'll show you what model we use to predict the noise. And you simply calculate the MSE loss between the actual noise and the predicted noise and backpropagate as always. And if you look at the code, the training code is really simple. All we are doing is we are saying, your x0 is some data. So we just picked it up from our data set. And then we also pick our time t randomly. And then we say, okay, give me noise, right? So add noise to my x0 for time step t. And now we say that my t normalized. Yeah, so one thing we do is so how you feed t into the neural network is also something that we should know. So usually when you want to feed t in, you would normalize it and just concatenate it. When you want to do that with, let's say, a CNN or a transformer, you would use a positional encoding, but more on that later. But here, all we are doing is we are normalizing it, and then we are passing it into our model. We have our xt, which we got from here, and we have our normalized t, which we got from here, and then we are predicting the noise. And then what we are doing is we are simply computing the loss between the predicted noise that our model gave and the original noise that we had computed here, right? So this is here. And we do backwards. And the training loop is probably the simplest of all the steps. And then after training, the hope is that, so this is the code that, once you kind of train it, and then each forward prop after you sample multiple times should give you one of these 2D points. And then if you do it enough number of times, you'll get the entire distribution of these x, y pairs, which should look like this Swiss roll that you see here.